Somewhere out in the galaxy right now, there are planets with no sun. They drift alone through the dark space between the stars, exposed to the freezing cold of the void, with no light warming their surface, and no day, night, or season to mark the passing of time. It's a genuinely alien way to exist. No sky to speak of, in any meaningful sense, no sunrise ever coming, nothing overhead but the same unmoving scatter of distant, indifferent stars for the entire span of the planet's existence. And yet, strange as it sounds, these lone wandering worlds might be carrying alien life to every corner of the galaxy. To understand how, it helps to first ask a simpler question. How does a planet end up alone in the first place? Astronomers use the term rogue planet for a few genuinely different things. Some are essentially failed stars, sub-brown dwarfs, gas giants that condensed directly out of a collapsing gas cloud rather than orbiting anything. And honestly, they're a bit boring, so that's the last we'll say about them. The far more interesting kind of rogue is a terrestrial planet, similar to Earth, that got violently kicked out of its own solar system. Finding these worlds at all is genuinely difficult, since they emit essentially no light of their own and don't orbit a star that could betray their presence through a telltale wobble or dip in brightness. The main technique that works is called gravitational microlensing. When a rogue planet happens to drift almost exactly between Earth and a distant background star, its gravity briefly bends and magnifies that star's light, creating a short, unmistakable flicker. Wide-field sky surveys have picked up dozens of these brief flickers over the years, and the statistics extracted from them are part of where estimates of a galaxy-wide rogue planet population in the billions actually come from. Young star systems are dangerous places. In the early chaos of formation, protoplanets compete fiercely for the same limited raw material, growing by devouring as much surrounding mass as they can. In that scramble for dominance, they collide with each other or drift dangerously close to one another's orbits. Our own solar system likely went through a milder version of this chaos itself. Many models of its early history suggest Jupiter and Saturn's orbits shifted substantially before settling into their current positions, and in the process may have flung smaller bodies out toward interstellar space entirely. If one particularly massive planet ends up migrating closer to its star, its gravity can be enough to fling a smaller planet clean out of the system entirely. And surviving that violent formative period isn't a guarantee of safety, either. A planetary system can still be disrupted at any later point by a close flyby from a passing star, or, more rarely, a black hole. Add it all up, and estimates suggest that as many as half of all planets that ever form could eventually end up as rogues. Scientists don't agree on the exact numbers, but even conservative estimates put the population of rogue planets in the Milky Way alone somewhere in the billions. Most of those wandering worlds share the same bleak fate. Cut off from their star's light, a planet's surface temperature plunges toward roughly minus 270 degrees Celsius, just a few degrees above absolute zero. Any oceans it once had freeze solid, turning as hard as bedrock. Even its atmosphere eventually sinks down and freezes onto the surface. It should, by any reasonable expectation, be a completely dead world. And yet, weirdly enough, some of these frozen, sunless deserts might actually be able to support life. To see how, imagine a planet roughly Earth's size and composition, and put it out in the dark of interstellar space. As far as science currently understands, life absolutely requires one non-negotiable ingredient: liquid water. Water matters because it's an extraordinarily good mixer, letting matter and energy combine and interact in ways that make complex chemistry, including the kind of chemistry that becomes life, actually possible. So the question becomes, without a sun, where would a planet like this even get the energy to keep any of its water liquid? Here's the part that makes rogue planets less hopeless than they first sound. Roughly 99.97% of the energy Earth receives normally comes from the sun, meaning our planet actually already runs on the remaining 0.03% for a meaningful part of its internal engine. Energy that comes almost entirely from its own hot interior. Earth's inner core is a solid metal ball, roughly as hot as the surface of the sun, surrounded by an outer core of liquid metal that's very slowly solidifying, a process that releases an enormous amount of heat as it happens. As long as that process continues, the planet stays geologically active, with molten and solid material constantly churning and carrying energy up toward the surface, where it can show up as geothermal heat. Every planet's core eventually cools down completely, but that process takes billions of years, more than enough time for life to get started and thrive in the meantime. There's an even more exotic possibility that could keep an Earth-like rogue planet's oceans from freezing over at all. If the planet happened to have an extremely dense, high-pressure hydrogen atmosphere, that gas wouldn't freeze even in deep space, and could trap enough outgoing heat to sustain liquid water reaching all the way up to the surface. And there's a completely different way to stay warm: moons. If a rogue planet manages to hold onto a large enough moon as it drifts away from its star, the gravitational tug-of-war between the two, tidal forces stretching and squeezing the planet slightly every single day, like a hand kneading dough, can generate a genuinely significant amount of extra internal heat all on its own. But the single most likely scenario for life on a rogue planet is something a little more modest: a subglacial ocean buried under a layer of water ice roughly a kilometer thick. This isn't some wild leap of imagination either. We already have several confirmed or strongly suspected examples of exactly this kind of hidden ocean right here in our own solar system. So how would life actually sustain itself at the bottom of a completely dark, permanently frozen ocean with no sunlight at all? Earth already has a working example. Deep in our own oceans, in total darkness, in volcanically active regions, there are hydrothermal vents known as black smokers, structures that spew out clouds of dark, mineral-rich, superheated water drawn up from Earth's mantle. Bacteria feed directly on those minerals through a process called chemosynthesis, essentially the dark ocean equivalent of photosynthesis, using chemical energy instead of sunlight to build organic material from scratch. That bacterial base then supports an entire food chain: crustaceans, bivalves, snails, fish, octopuses, and tube worms up to 2 meters long, all thriving without a single photon of sunlight, in water that would boil at the surface and pressure that would crush a submarine not built for it. These vents aren't just home to a strikingly diverse ecosystem. They're also one of the leading candidates for where life on Earth may have actually originated in the first place, billions of years ago. In the permanently dark ocean of a rogue planet, similar vents or volcanic activity could plausibly serve as the starting point for entire ecosystems we can currently only imagine. There's actually an upside to living in an ocean like that: extraordinary stability. A thick ice shell overhead shields the ocean from essentially every kind of surface catastrophe: asteroid impacts, radiation, climate swings, and as long as the planet's core keeps generating heat, conditions at the bottom stay remarkably consistent for an extremely long time, plausibly far longer than the roughly 4 billion years complex life has had to work with here on Earth, a planet that's been repeatedly reshaped by ice ages, mass extinctions, and shifting continents the entire way through. The most likely inhabitants would probably be bacteria and other simple microorganisms. But given enough time, there's no obvious reason more complex animals couldn't evolve to feed on those smaller organisms and thrive in turn. It's not even unreasonable to imagine intelligent life eventually emerging in an environment like that. If it did, it would find itself living in a genuinely strange world, boxed in by an impassable ceiling of rock-hard ice above and solid bedrock below, with no plants anywhere to have ever stored solar energy. There would be no wood, no oil, no coal, none of the stored, burnable energy that powered so much of human technological history. And even if there somehow were, it's hard to discover fire at the bottom of an ocean. Without fire, metals might never get smelted into useful tools in the first place. It's entirely possible that intelligent life in a place like this would never manage to break through the ice above them, might never even realize there's an outside to break through to, and simply assume their small, enclosed ocean is the entire universe. Millions of generations could be born, live, and die in those dark waters, layering culture on top of culture, completely unaware of the almost unimaginably vast universe sitting just a few kilometers above their heads. Eventually, the planet's core cools off for good. The ocean freezes solid from top to bottom, and everything, every civilization, every idea, every living thing gets sealed permanently into an icy grave. Honestly, there's a real argument that never knowing what they were missing might be a kind of mercy. But sitting with the concept a bit longer, it's both unsettling and strangely thrilling at the same time. The universe could genuinely be teeming with life, scattered across countless worlds that are, for all practical purposes, permanently sealed off from ever leaving, or even ever finding out there's anywhere else to go. It raises an odd, almost vertiginous question about our own situation too. How would anyone down there ever really know whether their entire universe was actually much larger than a frozen ceiling of ice? For all we can say, with total confidence, nothing rules out some equivalent uncertainty applying to us. On some scale, we simply haven't found a way to test yet. Planets exactly like this could already be drifting silently past our own solar system on a regular basis, and we would have no way of knowing. Maybe, someday, in the distant future, humans will actually set foot on one of these frozen, drifting worlds, drill down through kilometers of ice into an ocean that's never once seen light, and try, somehow, to say hello. Hello,